I work a lot with spin system mainly, and so solid state system, especially decoherence, is a huge problem. And of course, if you want to build a quantum computer, decoherence is your enemy. So it's better to know your enemy. So what I'll try to do today is talk a bit about how you can, what you can think about decoherence, what is its physical meaning, ways of sort of representing it mathematically, because of course when you want to model decoherence and being able to predict how your system will behave, and then in the end I will talk a bit what we can do to fight decoherence. I'm sure you will learn more about quantum error correction in some other lectures, so I'm not going to do that, but I will talk about some other techniques. So before I start, I just will do a bit of advertisement about myself and what I do. Hopefully you're interested. Okay. So switching colors, which probably will not work very well. But so as Martin was saying, I'm at MIT now, and I've because my last name is impossible to spell unless you're Italian, so I couldn't call my lab the Cappellaro group because then nobody would have been able to remember or write it down. So I call it the Quantum Engineering Group, or KEG if you like beers. And we are at MIT. I don't like beer, so yeah, the joke is on me because I call it KEG, but I don't like beer. Oh well. We are at MIT. I'm in the Nuclear Science and Engineering department. And I collaborate with a lot of people around MIT. We have various groups. For example, IQIC is sort of a center which is around quantum information. And so it sort of tries to sort of propose a curriculum for graduate studies in quantum information, bringing together different departments. So what do we do in the KEG group? We're sort of trying to have fun with quantum information. So we want to play around with these ideas. And so we want to have the Lego approach to quantum information processing. So, which means two things. One, having fun with it. And two, sort of trying to build up a quantum computer, a quantum information processor, starting from small building blocks and then putting them together to build something bigger. And the problem is that, of course, as you're learning here, or maybe you already know, is that it's very difficult to have a scalable, large quantum system which you can use as a computer. And so instead of trying to go directly for the big quantum computer, what we are trying to say is, OK, let's work on very small building blocks. Let's try to perfect their control as much as possible, know how to fight decoherence, things that we will look at today. And then just when you have very good control on everything, just build them, put them together so that you can build something much bigger and have a scalable quantum processor. So what do we use as our building blocks? As Martin was saying, we use, well, we have been, like from the point of view of experiment, we use nitrogen vacancy center in Diamond. And I think that you probably had a lecture about this by David Corey. And so while it's this color center, you see a little pink dot there. So at some point, we had this fantastic diamond. I mean, if you like diamonds, they were like bright pink because they had so many envy centers. Unfortunately, so it's by a company called Apollo, which is close by MIT. Fortunately, we had to give them back, but they were really, really amazing. Anyway, too bad. Normally, like our diamond, like little chip, like 3 millimeter square, yellow. Like, don't look anything like this. But they're still amazing for doing science, which is good. So you have your nitrogen and vacancy close by. You look in confocal microscopy. You see some bright spot, and these one are single electronic spin. And then, of course, we can control them. So we have the sort of the optical levels. And then we work in using ESR to control, for example, one qubit here, the 0 and the +1. And the interesting thing is that, of course, we have a lot of carbon-13 around here. And so we can use these as extra qubits. And so what we will have is a small quantum register, which is local, and we can really hope to control it very well, because the MV center have amazing coherence properties, so very long coherence time. Nuclear spin, they usually do have very long coherence time, but then it's very difficult to control them. But now what you have is here this handle given by the MV center, which allows you to control some individual nuclear spin. And so this is really, if you want, a very good starting point to have this small quantum register, with small building blocks for my Lego approach. And then what we want to do at some point is, of course, to scale them up. So I will have one of the MV center with the nearby nuclear spin here. Another one is another location of my diamond, and I want sort of to couple them together. So one thing that I can use, since if I just want to stay inside my solid-state system, is to use other spin, which are in my diamond lattice. For example, electronic nitrogen spins, which you create at the same time when you create MV centers, and use them as wires to connect the various registers. So this will be like the way of building up a larger system. So this is a second theme of our research. And instead of starting directly with sort of transport or like communication through the spin in the diamond system, we use solid state NMR to sort of simulate the same problem, but with a system which is much better understood. So the main advantage is that I really know where my spin will be if I use a crystal in which all the spin of interest, all the nuclei of interest do have a spin. So for the diamond, you have just some impurities which have your electronic spin, but you don't know where they are. So it's like a very complex random system. It's not like the picture that I showed before where we were in nice arrays, but still very difficult to achieve. People are working on implanting with very high precision, but we are not there. So we use a crystal in which the spin are just in the location given by nature, so you know where they are. So this crystal is fluorapatite, so it looks like this. So this one is this material fluorapatite, and actually it's a sample which I bought for $10 on eBay. So people use it as a pendant, but I think that it's much better use for quantum information. Still is much cheaper than using diamond, yes. And this is like the lattice structure, but the interesting thing is that this red sphere, they're like fluorine nuclear spin 1/2. And if you stack many of these together, what you see emerging here is really like a linear chain of spin in this vertical direction. And the distance to the next chain is large enough that the ratio of the coupling in chain to cross chain is like around 40. So you really have something which looks like a 1D system. And so we can use that to simulate transport or simulate other things like some many-body physics. Again, decoherence, looking at this system, which is a bit cleaner because it's a 1D system instead of the usual mess of solid-state 3D system. So finally, the last thing that we do is to look at problem of, in general, quantum metrologies. How can you use a quantum system instead of building a quantum computer as quantum sensors? And they are supposed to be much more sensitive if you can sort of exploit their quantumness. But even if you just use them as a single qubit spin probe, most probably you will be able to, for example, have a much smaller system at the nanoscale, and that's already an advantage with respect to other classical probes. And so we look at, for example, magnetic field sensing with MV. Now we are thinking about using it as a gyroscope. So, for example, if you have a Wii, you have gyroscope, or an iPhone, then maybe we will have a gyroscope made up of an MV center in diamond. Okay, and this is the people who are working right now. So I'm a very student, and this is what happened. Oops, I don't have the other picture, I guess. I forgot. I have it. Everybody after this picture were just jumping out, and it was a mess. But we're always looking for good students to come and join us. So maybe when you graduate. But today, we are going to talk instead about decoherence. So unless you have a question on whatever the keg is doing, I will move on onto this. No question? Is it interesting? It's cool. It is cool. I think I left my notes here. I should read. Okay. So, decoherence. What is decoherence? Do you know? Who knows what is decoherence? Guess.
Actually, I have a question. Not answer. I'm just wondering, regarding diamond NV centers, is it the goal to create a crystal which has many like NV centers, or which has like one NV center per crystal?
It depends what you want to do with it. So, for example, if your goal is to study with little quantum register, so you want maybe one NV center and you want to really sort of push to the limit like your control techniques. So then maybe you want to start with a diamond which has nothing inside except one NV center, maybe one or two carbon-14 nearby, but the rest of the diamond is even isotopically purified carbon-12, so it doesn't have any spin. So your coherence time are going to be ages, and then you can start playing around with your control. Maybe you want to study instead how to find decoherence. Then if you don't have any decoherence, well, that's not the way to go. Maybe you want to study how to couple two different NVs, so then maybe you want to have more than one, and so it's difficult to just have two. Maybe you will have a bit more. For example, for metrology, maybe you just want to use one NV center and have very long coherence time, or another regime is you have many, many NV center, of course, like the signal goes up as the number of the NV center themselves, so there is like sort of a trade-off because you have shorter coherence time, but a larger signal coming from many. So there's not one single goal, of course. There are many different goals, and then what material scientists are doing is sort of like to adapt to all our requests for, okay, now I want one with only carbon-12, now one with all carbon-14, now I want a lot, little. So, yeah, and that's what it's fun, but you can really have many different type of materials. Other questions? So now I'm asking again the question, what is decoherence? Decoherence. It doesn't have to be the correct answer or even very precise.
Loss of information from a system to the environment.
Wow, that's already very fancy. Loss of information. System to environment. There was another down there.
If your system gets entangled with the environment so that you have to treat what you're controlling as a mixed state.
Okay. So we have system plus environment get entangled. So system alone is mixed. Okay.
Coherence means that when you have two states and you want to do some superposition as you do in waves, then you'll get the new state, and it's where all the fancy quantum stuff come from. And but the coherence means when you're losing that superposition and you're dealing with some classical probability like this and this.
So I think that you're saying two things. One is loss of fancy quantum stuff, which I think it's very appropriate. Oh, I forgot fancy. Let's see. Quantum stuff. So it's a bit of like quantum to classical transition, if you want. Yeah, if I had to rewrite it down. Okay. And the second thing that you were saying is, well, if you want to define decoherence, I should define first what is coherence, which seems a very good idea. And so you're saying, well, coherence is when you have some sort of phase coherence between different, for example, state or like in a superposition state, and then when I lose that, then that's when decoherence is appearing. So we can just say loss of phase coherence if you want. So you guys know already everything. Do I really need to teach you something? I think that like any of these is a very good definition of what decoherence is. And there are still actually debates on what people define as decoherence. For example, some people do not call decoherence if you are interacting with a classical bath because, well, you cannot get your system entangled with a classical bath because, well, it's not quantum, what is the entanglement? And some other people are like, well, whatever. I'm still getting my loss of coherence even if I'm interacting with a classical bath, so I will just call it decoherence. So I'm not going to be particularly strict about what is the correct definition because, as I say, like there are people debating on it. So, well, for me, it's if you want, yes, I have a loss of phase coherence. This is the most general, if you want, the definition that you can have. More precisely, you would like to have some sort of idea of getting your system entangled with your environment, and then if you're looking only at your system, you will lose some of the information which was sort of carried by this entanglement, and so you will get that your system becomes just a mixed state, so you lose some of its phase coherence in that process. So what we're going to do is really trying to have a bit of a more precise look at all of these and see how it plays out in a bit more detail. But I think that, like, you guys already know everything. Why should I explain stuff? So what do we want to learn today? So in my point of view, I mean, this is not like the outline, but just like what you should get out of here today is a bit of this physical intuition of what decoherence is. And as I said, it's a bit you already know that. But maybe we will see a bit more example and put some more details on it. The other things is a bit having some idea on how we will sort of trying to model decoherence if you want to predict things quantitatively or qualitatively, while you still want some kind of model so that you will be able to predict what the evolution of your system is in the presence of an environment. And I will try to sort of make some physical examples without really like something very, very precise, but hopefully you can relate to some of the labs that you're doing or some of the other lecture that you're listening here. So I think last slide. So what I'm going to talk a bit today, and then I will try to ask you also like what you already know and what not, to see what cover faster or slower. But the idea is to sort of start a bit maybe with this concept that you have a composite system, so an open system in which you have your real system interacting with an environment, and they will get in some way entangled, and so you will get a mixed state out of it. And so this is sort of this fourth part here, and also how entanglement related to the fact that you will get a mixed state in the end. And then the second part is a bit more, okay, this could be just a static picture. We don't have really a dynamics in here. So how we input the dynamics and how that then can be written down, and what are some sort of models in which you can have sort of what type of environment you could have, what type of interaction. And so this is, it's already, if you want some mathematical model on how to describe your decoherence, but it's often not a very practical mathematical model. So since I was supposed to teach something practical about decoherence, so then we will look a bit more at the master equation, which is a bit better practical way of describing your decoherence. And then, as I said at the end, I would also like to give you just a hint of how can we fight decoherence. And you do have like electron quantum error correction, yeah? Yeah, so I'm not going to talk about that because it's a huge topic. There are other ways of fighting decoherence. Besides quantum error correction, you can try to use some subsystem of your total system which are inherently protected against decoherence, so they do not decay. Or the third way is to use dynamical decoupling. So we'll talk a bit about the dynamical decoupling because I think it's the one which sort of relates better to this type of description of your of decoherence. You probably know that in quantum mechanics, one of the axiom, if you want, of the principle of quantum mechanics is that maybe like the fourth principle or axiom is that all information about your system is contained in more general. It's quantum. Yes, for example, quantum mechanics is not just quantum information, although we could try, but well, not everybody's going to be happy. So yes, all information about the system. I think at some point I'm going to remove it. The system. State vector that in Dirac notation we will call psi. Okay, just everybody call it psi. So, but the question now is, this is all information, which means all possible information that will be ever possible to know about it. So there is no other information that could ever be learned about it. So what if we don't have all possible information about a system? What do we do then? How do we describe our system? So what if not all info is available? So what represents our system then? So this is what I normally do with my students. I just like stand here and point to the answer and hope that somebody will be brave enough to just read it out. Yes, so thank you. At least you're brave. Thank you. Kumawo. So we can use a density operator or density matrix because it's often represented mathematically by a matrix. Will give all the information that we have about the system. So in this case, it's not all the possible information about the system, it's only the information which is available to us. Okay, and you probably have already seen the density operator, yes? So I'm not gonna really I'll try just to go quickly, but I just wanted to have a few reminders so that we will be using it later on. So in particular, let's say that we want to have like a mathematical description of this density operator. What are the important mathematical characteristics of the density operator? Perfect. Trace of rho is equal to 1. What is, if I have a pure state? Or something. I didn't really heard you, but I think that what you said is psi cross psi or something like this. Yes? Okay, so it's the outer product of psi. We have other property. For example, it is Hermitian. So rho dagger is equal to rho. It is non-negative, so we have negative. So if I take any vector u, rho u rho is larger or equal to 0. Okay. So how can we then use this density operator to describe our system? We have, if you want, beside the first axiom, when in quantum mechanics you can have like the other 3 axioms usually. Therefore, I guess it depends like how people present it, more or less, which describe how you get out like measurement outcomes, what is the evolution of your system, and so on and so forth. So we can do sort of the same thing in terms of the density operator. Okay. So what we want to know is, for example, what is expectation values of observables. Oops. So what will this given by? So if I have a pure state, hold that thought. If I have a pure state, what is given by? for my pure state psi. Okay, I hear some murmurs. You should speak up. Did I write it correctly? So if instead I have a mixed state, then it's trace of whatever my observable is times my density operator. Perfect. Okay. Then what else do we want to know? Well, I'd like to know what is the evolution of my system. So which equation gives me the evolution of a pure state system? Oh, I knew it at least for once. I would get like a chorus. Good. So what about now my density operator? So I want what is d rho dt. So what is it? All my h bar are 1. Yes? H bar is 1. Does everybody agree here that h bar is 1? Perfect. Thank you. Thank you. Otherwise, I will just like put them somewhere and then forget them. So, okay, h bar is 1. I like it. Thank you. Yes. I have to teach also quantum physics to nuclear physicists. And for them, h bar is not 1, unfortunately. And yes, it's very difficult. Yes. Anyway, so h bar is 1. So this is all that we have for our Liouville equation. So it's the commutator of our Hamiltonian with the density operator itself. Okay. And then I can also, for example, be interested in knowing what is just rho at some time t as a function of what was rho, for example, at time 0. So how do I write this down? More precisely. I didn't get it. It's probably correct. I just didn't get it. You conjugate it by the evolution operator. So, well, I normally write it down like this. So where u is for time-independent Hamiltonian will be something like e to the minus I a ht. So your propagator or evolution operator is an e. Okay. For Hamiltonian, which vary in time, you will have like some time ordinary operator. But okay. Okay. So perfect. So we know now how to deal with density operators. Okay, but we haven't really looked so much at what actually it means to have a density operator. So how can we sort of interpret the density operator? So what I introduced it by saying, well, if we don't have all the possible information about our system, we might want to use the density operator. Okay, but what does it mean more exactly that I don't have all the information about my system? So if I write here, probably all you guys are going to have a head, neck pain. So I will just start erasing. Okay, so remember this relationship. Okay, write it down. Or just write it in your brain. We will use it. Everything else, also remember it, but maybe we'll use it a bit less. Okay. So we know all the math detail of the density operator, but we still don't know what exactly it means. Maybe I should have started with the meaning first. But if you get all the difficult math part out of the way, then you're like relaxed and you know, okay, I can focus on the important part now. Okay. Oops. So there are various ways in which you can sort of introduce or interpret your density operator. So you can sort of give it slightly different meanings in different situations. So the first one, if you want, is sort of the same that I was telling you before. So I have a system, okay, but I don't know if the system, so I have one system, but I don't know if it's in one pure state psi 1, or if it's in a different pure state psi 2, for example. Okay. And I can say that with some probability P1, it's in the state psi 1, and with probability P2, is instead in the state psi 2. Okay. So what I'm describing here is a situation in which I have a system, but I don't have all the information about the system. If I knew that the system was in psi 1, then I would have all the possible information about the system. But I have this uncertainty between which one of the two it is. So then to describe the system, what I can do is to write down as this density operator, which is going to be given by this side of the class. I think that this side is answering more, so somebody on this side.
The sum of each, like the other product of each possible
Perfect.
state times its probability.
So it would be pi P1, psi 1, plus probability 2, oops, psi 2, psi 2. Okay, and in general, if I have many possible states with different probabilities, so rho is going to be given by sum over j of probability j, or some psi j, psi j. Okay, and it could even be, for example, a continuous distribution. So it's easier to write it down as a discrete distribution, but it could also be a continuous distribution if psi depends on some continuous parameter. So this is probably the most common way of introducing density operator, at least that's what I think. And it sort of tells us immediately that while if I want to have a pure state, what I need is one pj equal to 1, and all the other ones h different than j equal to 0. In that case, I will go back to having just one of these. So it represents the fact that I do know that my system is in this particular state, and so I know everything that is there to know about the system. Okay. So a second way, so if you want this sort of represent my ignorance, my lack of knowledge about the system. Okay. A second way of thinking about the density operator is the case in which I have some state, which is an ensemble of many possible microsystems. But I can only know properties of the macro system. So this is, if you have had statistical mechanics, this is sort of like the same idea of statistical ensembles. Okay. So to describe your macro system composed of this ensemble, I can use this density operator. Okay. So I have a statistical ensemble, and I can only know or have information on the macro system. And again, I will have that this macro system is described by probability distribution over possible microsystem. So I will have a probability distribution of microsystem, macrostates. I should state the macrostate here as well. And so again, I will have that this can be represented by density operator as sum over pj psi j, for example. where this probability now describes this statistical ensemble. So this is, if you want, very similar to this, but what is underlined here is the fact that I'm thinking about an ensemble, while here I was just like sort of reflecting my lack of knowledge. And it's sort of also the same way in which you can introduce probability in two different ways, either with ensemble or as lack of knowledge. So we're sort of reflecting that, that fact. And for example, in this sort of point of view, you can start looking at quantum statistical theory and introduce all kinds of like ensembles, like macrocanonic ensemble, et cetera, et cetera. Yes?
The statistical ensemble, so oftentimes you take it, like you assume it's like a continuous, like there's so many that like all your properties are continuous. So does your density matrix just become like a probability distribution function times?
Yeah, I mean, you can, so as I say, like for convenience, just because it's easier to think in terms of a sum of discrete state labeled by J, here I put a sum. But this psi J could be just, if you want, a statistic, like a continuous function of some parameter, and then you will have like integral over a probability distribution of your psi. So that's totally possible, yeah. Okay.
Or what is U state?
Or macro state. Macro state. Mu is always macro for anything. Sorry. Thanks for interrupting me, because yes, something. Yeah, but thanks. Yeah, it's not very clear. Okay, so then the third case in which density operator arise is when I have a large system but I'm only interested, or maybe even more precisely, I can only know part of this large system. So I have some very large quantum system, which might be very well represented by a density, a pure state. But all that I can know is this small subsystem inside here. And then what I would like to know, sort of have a representation of all the information that I have about this smaller system alone here. Okay, so I have a large system, but I can only know a smaller part of it. And then I guess this is something that I think Martin has introduced to you. So what you do is to say, well, I have that system psi, how can I, which represent everything, and just to, since we're going to talk about decoherence, what I will say is that this is my system, and the rest, which is not the system, I will call it environment, for example. So this pure state represents the system plus environment total system. Okay. So from this, I would like to get some representation for my system alone. This will be given by a density operator. And how do I get this? Starting from, if I really knew what was the pure state describing the system plus environment system, how would I get just the state of my system alone? Trace out environment. Perfect. So I do a partial trace, which I normally write down with just like the subscript indicating what I'm tracing out of. What I want to do is trace out this. I write it down in terms of the outer product. So this is the same as if you want the density operator describing the system plus environment. And then I will get out just the information about the system.
So you know both system wave function and system plus environment wave function.
So in this fiction, which is probably not ever going to happen, I'm saying that, yes, I knew at the beginning my system plus environment wave function or state, which is in a pure state. And then I say, if I only am interested in the system, because I don't care about the environment, then how can I write down mathematically something which will describe the state of my system? Then what I do is to take the partial trace, so disregard anything which is describing the environment, and just take the part which is describing the system. So usually you actually do not know what was your system plus environment, so naturally what you will have is that your system will be described by a density operator to start with, which you might think, so in other words, if you want, if I give you, so if I give some density operator rho s describing a system, you can always build a fictional environment and a minimal environment which is such that, so you can always find an environment such that you can build a pure state psi system plus environment that when you do the partial trace off will give you back rho s. Okay, so you do partial trace this and you can go back here. This fictional environment might have nothing to do with the real environment, which at the beginning gave you this rho s. Okay. It might be useful to do some modeling, or it might just be like a mathematical fiction if you want. But it's always possible to do it. Usually you are really interested only in your system because the environment is so large, so complex that you cannot really know what its state is. And that's why you're only interested in this part here. So as I say, like the fact to start with this psi SE, it's, well, not really something practical. Okay, but conceptually, this is what you will get. So we talked about partial trace. So let's say that our psi, the state vector describing the system and environment, it's going to be given by some sum over some coefficients, ij, alpha ij, psi I of the system, tensor product psi j of the environment. Okay. So what is rho s? Write it down and let me know. So what is the first thing that you would do?
Create the density matrix of the system.
Okay, so you have psi SE. What you want to do is to do the outer product. So you will have psi SE, psi SE. So, well, you have to take this and just do everything. Okay, so it will be, okay, this is already a double sum, as I brought it down, so it will be like 4 sums. Okay, sum over 4 indexes. So it will be, let's call it sum ij, sum kh. Okay, so I can write down these same things. Alpha ij, psi I, psi j, system environment. And then I have the outer product with the same thing, complex conjugate. So I will have some alpha j, alpha complex conjugate, kh of psi k on the system, psi h on the environment. Okay. So this is written very badly. Let me reorganize so that it's written. I mean, beside my usual problem with writing down. I have a Japanese student, yes, Masashi. He writes so beautifully. Okay. So anytime that we have to write down something nicely, then it's like, Masashi, come here. But for me, it's very, very bad. Anyway. So you can write it down this way, ij, kh, alpha ij, alpha complex conjugate, kh. Yes, my k and h also look the same. That's another problem with my writing, which doesn't help. Even myself, because when I do calculation, then I always forget my indexes because they all get messed up. So I have my system will be psi I, psi k, as I called it. is the system, tensor product, psi j, psi h on the environment. Did I do it wrong?
KH should be HK since you are using
So
upper.
K. This is the first one was a K, the second one was a H.
Because you do conjugate, so that it should be HK.
Oh, okay, yeah, but yeah, sure, but yeah, it's the same. I mean, the K just refers to the system and the H to the environment, so they're not really matrices if you want. It's just like the index for one, the system and the environment. So now I want to do the partial trace of this thing here. Okay, so I want to do the trace over the environment of all this stuff here. This is already written down as sum over various terms in which I have my system, if you want the density operator, and environment density operator. Okay, so if you have the partial trace of something which is written like this, what is this equal to? Rho s. Perfect. What if, let's call it, let's say that A is not a density operator. So it will be the trace of AE. Okay. Okay, perfect. So just because here we might not have it with our density operator per se. Okay, so then, well, I'm almost done. So I will add some of my ij, kh, ij, alpha, kh, psi I, psi j, and then trace of this term here. Oops, I wrote it wrong. Okay, psi j, psi h. Okay. So of course the sum over kh I could make sort of explicitly. So what I have in the end, it will be some coefficient which is alpha j times sum of kh. Sorry, sum of ik, sum over hj of my. I should take it out. J alpha kh plus conjugate and this trace of psi j, psi h. My environment, sum over ki, and then I have psi I, psi k of the system. So all of these is just like some numerical coefficient. So this again, because I'm doing this trace, I will only pick up the terms which are diagonal. So in the end, I will get just my usual diagonal, like my usual mixed state. Okay. So this, because I have like various sum of this term here, then it will be sort of similar to a sum like what I have here, and I'm expecting the general case to have a mixed state and not a pure state. So I will not just have one single pure state. Okay. So yes, if I start from something like this, I will get out something which looks like a mixed state. Okay. So again, the ways of taking the partial trace is to sort of write down everything so that you have a sum of terms which only depend on the system, let's say, and another part which only depend on environment, so that you can sort of apply the partial trace directly on the second part, for example. Okay, so you always want to write it down in this sort of separate sum of separable states. Okay. So besides this slash of math, let's go back to our three main meanings, if you want, of the density operator. And do they have something in common? So as I brought them down, likely enough, they have some sort of common themes. So the first one, I don't know if it's in Psi1 or Psi2. Actually, no, I didn't copy what I was here. It was actually different. So I was lucky that even if invented, it still came out all right. So the second one is I can only know, okay. And here, well, okay, I use the same phrase. I guess that by the third time I got smarter and I wanted to point out that something similar was coming. So even there, I can only know a smaller part of it. So these three ways of looking at density matrix, they sort of all the same. They sort of reflect our lack of knowledge about our system. Okay, and it can be sort of like a lack of knowledge which was already there, or that we are sort of losing because we are disregarding part of our system. And when you look at decoherence, this last sort of way of looking at your density operator is the one which is going to be, if you want, the more important. Because what is going to be decoherence? Well, you can think that maybe I have initially my system and environment, which are there, but they are not talking to each other, so they are separate. And then if you go through this whole mess, and I will give you another problem in a second, you will notice that if the two are not interacting, they're not entangled, your system will still be in a pure state. So you will still have all possible knowledge. And that's very intuitive. So if you don't have any correlation between your system and environment, then you can know your system perfectly, even if you don't know anything about the environment. But if you do have some correlation between the two, doing the partial trace sort of kills this correlation, sort of disregarded. Like you throw it in the trash, and then, well, you are losing some information, so you will have something which looks like a mixed state. Okay. And what is decoherence is nothing else, well, but if you start with something which is separate, then during the evolution you will create this correlation between the two, and then at some point you sort of throw it away. So again, you will lose the fact that you had a pure state with a phase coherence, and you will lose it and find a mixed state in which, at the end of the day, all phase coherence might be lost. Okay? So this sort of third point of view is the one which is maybe more relevant for decoherence, although even this other one, they can come back and sort of lead to slightly different ways of presenting decoherence. Okay. Yes?
Is there any difference between you know the states and you don't know the states in terms of density operator or other operation?
What do you mean by? So I mean, it's not that I don't know anything about my state. I only have some partial knowledge. So if I don't know anything about my state, there is, if you want, one way of representing that fact. I'll erase this, too much math. So if I don't know anything about the system, okay, what it means is that I have all possible state, sum over psi I, okay, with I going from 1 to n, where n is the total number of possible states. And all of them will have the same probability, 1 over n. It's sort of like the same as a uniform probability distribution, sort of. It sort of describe your complete lack of knowledge about your system. Okay, and this is nothing else than the identity operator normalized by the dimension of your system, and this sort of represent your complete lack of knowledge about the system itself. So this is, if you want, is complete ignorance. Okay, more or less, it's the same probability of being in any possible state. So in some sense, I can still describe it with a density operator. But I'm not sure that was your question, though.
What I mean by is that when I do like optics experiments, like I'm curious about if I prepare two superposition of the states.
Yes.
And use that, or if I had like either one state with the same probability.
That's a very good question. Let's see. Let's see.
I wonder how
let's see if I got it right. So maybe what you're asking is the following. Let's say that I have a state in which I'm having my qubit in this superposition, 0 or 1. Let's normalize it for the sake of it. Can I distinguish this with the different case of this state in which I do have all the possible information about my state is in here? Okay? And instead I have another state, which is a density operator, in which I, instead of having this coherent superposition, I have an incoherent sum of the two. So I have, for example, 0, 0 plus 1, 1 over 2. Is this closer to what you were asking or not? Okay, so how can I know if I have this kind of state or this other kind of state? So how do I know if I do have knowledge about my system or not? Okay, so you could try to measure different things. Okay, so here let's say that this 0 and 1 represent your qubit, okay, and you saw the polymatrices, yeah? Okay, so you want to measure, for example, sigma z. Okay, what is the expectation value of sigma z in these two cases?
Upper one is half.
The upper one is half.
Both will have the same expectation for sigma z.
Which is
0.
yes. So this one, like you have with 1/2 probability, you are in the pointing up state, and 1/2 probability is in the pointing down state. So on average, your sigma z, your polarization along the z direction is 0. Okay. So in this case, it's 0, and in this other case, this is again trace of rho sigma z. This is just again the identity, so a trace of sigma z, which is 0. Okay. So in some sense, let's say that you do the following experiment. You create your state. Okay. You don't know which one of the two you are creating, and then you measure the expectation value of sigma z. You get the same result. Okay. Why? How can I distinguish them? So what you can do is to do a different type of experiment. Okay, so what if I measure now sigma x? What is the expectation value in the first case? So it's like 1 and sigma x in the second case. Let's start with 2, which is easy. What is 2? You know, okay. Is it clear to everybody? So again, it's like sigma x times this. This is, again, just the identity, but the trace of sigma x is also 0. Okay. What about this now?
1.
Because this, what it represents, is just one eigenstate with eigenvalue plus 1 of sigma x itself. Okay. So by doing these two experiments, okay, you can distinguish if you had a coherent superposition or something which tells you, well, you don't know anything about your state. Okay. So there are ways, like experimental ways, of really distinguishing between what your preparation gave you. In some sense. Is this closer to what you were asking? Yeah. Okay. I got it right. Yes. So, in some sense, this is very typical. Like when you have a mixed state, you measure different things. I mean, it's not that always you get the same result, of course, but you sort of can distinguish between the two cases if you do the correct measurement. So just doing one measurement sometimes is not enough to really, of course, determine what your state is. And you might have heard about like state tomography, so you need to do more measurements, and this will allow you to really know what your state is. Okay. What time is it? Another small problem for you guys. This time is much easier, actually. So let's say that I have two states. First state is the following. Psi 1 is equal to, let's talk qubits of 0, 1 state, okay? Plus 1, 1. Over square root of 2, and the first qubit, it's our system, and second qubit is the environment. Okay, and then I have another state, which is, let's say, 0, 1 plus 1, 1 over square root of 2. Okay. So if I trace over my environment, so if I do the partial trace over the environment of 1 and 2, which one will give me a mixed state and which one will not give me a mixed state? Okay. Who? Let's see again if you're brave. Like, who? Raise your hand for the first one is mixed. Ah, you're good. Okay. I mean, besides giving a correct or wrong answer, like the fact that you raise your hands is really good. I never managed to get people to do that. I mean, okay. What about the second one? Raise your hands if you think that it will be mixed. Okay, let's try it. Raise your hand if you think that it will be pure, so at least we know if you're answering or not. Okay, so some people are not sure. So, well, which is good. Okay, so the point is, well, how do you know something is mixed? I haven't really told you. You might have heard already, but I didn't really tell you. So, when is rho mixed? So when, okay, in better words, when does your density operator represent a mixed state? Okay, we know that we can write a pure state as a density operator, so not all density operators need to be mixed state. Okay, how do we know if a particular density operator is representing a mixed state? There is a very simple test for it. Did you guys see?
Diagonal term.
Okay, so yes, I could, for example, diagonalize. It's not a very simple test. I could, I mean, let's say that I give you like, I don't know, 15 qubit system, and then I give you like a density operator, and I tell you, okay, tell me that is that pure or mixed. Then what you're going to do is to diagonalize as 2 to the 15 times 2 to the 15 matrix, and then see what it is. Not practical. We are talking practical today. So yes, I could diagonalize. So if I diagonalize and then check if I only have one non-zero eigenvalue, it would mean that really my rho could be written in corresponding eigenvector psi. My rho could be written in terms of this psi. This is a good way, but not practical unless you have a 2 by 2 matrix which you can diagonalize by hand. Especially if I ask you to do it on the board, then yes, we will talk.
Trace of rho squared.
Perfect. Okay, so a simpler test. I'm not saying that like a 2 by 15, like 2 by 15, you can do trace of rho square on a board, but still it is easier when diagonalizing. So trace rho square, if it's equal to 1, correspond to a pure state. Okay. If it's less than 1, then it's mixed. Okay. So why is that? Oops. So let's say that I have some rho which is, as we had before, P1, psi1, psi1, plus P2, psi2, psi2. Okay. What is then rho square and trace of rho square? So I have to calculate rho square, I have to rho times rho. Okay. But then I only care about like the diagonal part of this rho. So what I'm interested in is trace of, well, I will have this P1 square times psi1, 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 psi1. I can say that this is just 1, okay, if I have normalized states, okay. Plus, I could have things like, let's say, P1, P2, psi1, psi1, psi2, psi2, but then this is not diagonal because psi1 different than psi2, so this one is 0. So the second part is just P2 square, psi2, psi2. Okay? And so this is just P1 square plus P2 square. Okay? So because we know that in this interpretation P1 are probabilities, or in any case we know that trace of rho is equal to 1, then it means that this P1 and P2 have to be less or equal to 1, and so the sum of P1 square plus P2 square will be less or equal than 1. Okay? So I can also write it down as P1 square plus 1 minus P1 square. So when is this going to be equal to 1? Yes. So if P1 is 1, then P2 has to be equal to 0. So then I have 1, or the opposite. P1 is 0, meaning that P2 is 1. But what does this mean? Well, what I really had in that case was just a pure state, because I only had one of these terms here. Okay. So this trace of rho square, which is sometimes called purity, it's a good metric of how mixed your state is. And the first function is just to distinguish between pure or mixed states. Okay. So of course, here I did it for just 2 possible states, but you can just generalize very quickly to the sum of many possible states. Just more math involved, but it's still the same. Okay. Okay, so we know now how to calculate if our state is going to be mixed or not. So what I could do then is go back to this state here, okay, take the partial trace, and whatever I get in the end, apply this test to know if it's pure or not. Okay, so if you want to do everything like very straightforward, you can just do all these steps here. Okay. The second thing that you can also look at is that the second state, I wrote it down in that way, but I could simplify it a bit. Okay, so this is not going to give me a mixed state when I trace over the environment, just because I can rewrite psi2 in the following way. 0 plus 1 over square root of 2, tensor product 1. Okay, so this is my system again, and this is my environment. So what I had is that, well, besides writing it down in this way to confuse you, okay, but I really had just a separable state between my system and environment. Okay, so when I write down my in density operator form, I can also write it down as rho system times 1, 1, where this rho system is just like all ones times 1 half. Okay. So then if I do the partial trace of this, well, I just taking out this part, and I will just get my rho s, which is nothing else than writing down this first term here as an outer product, but it's still a pure state. Okay. This other state instead, you might have recognized as one particular state, which is called. Okay, almost good, almost good. I can hear a bit more from this side. You could be a bit louder. So this is one of the Bell pairs, yes, Bell state. And so we know that this state instead, it is entangled. Okay, so it does have entanglement between the system and environment. So we do expect then, when doing the partial trace, we will lose some knowledge about this correlation between the two, and so we will get some mixed state. In particular, from psi1, when I do the partial trace, what I actually get is the identity operator, divided by 2 in this case, because I have a true system, which tells me that in doing these partial trace, I lost all possible knowledge about my system, because we discussed before that this identity state just meant that I have no knowledge at all of my system. And in some, if you want reciprocally, what it's saying is that this state was maximally mixed, because I have so much entanglement, so much correlation about my system and environment, that when I lose any knowledge about my system, I lose any possible knowledge also about my system. It's just reduced to something which represents my complete ignorance. Okay, so there is a strong relationship, if you want, between entanglement and mixedness of the reduced state. Okay, so if I do have entanglement between my system and environment, or two systems, if you talk about qubits, when I discard information about my environment, I will get out some mixed reduced state. Okay, and again, it's because I'm really neglecting some kind of correlation. So because of the correlation, I cannot just describe my system alone as a separate things from the environment. To have a full knowledge, I should describe the two of them together. Okay, so we have our block sphere. And what I just wanted to show you is that you can have different ways of representing your qubit. Okay, so if it's a pure state, you can have it in the form of a state vector. You can still write it down as your density operator in terms of a matrix, or you could have it written down in terms of a basis given, for example, by the Pauli matrix. And if you want this last basis, the one which sort of is better represented in this block sphere, in which you're sort of representing the projection onto the three Pauli matrix x, sigma, y, sigma, z as the coordinates, if you want, of your sphere. Okay? So, for example, I can change my angle theta, and you will start having a superposition between the 0 and 1 state. And here I have sort of superposition between sigma x and sigma z basis state. And well, your matrix, this is what it looks like. And then I can also start rotating my vector with a phi angle. And so rotating it around, and you see that like you start having like a phase here with respect to my 0 and 1 state, rotating around, and here I start having my sigma y type of state here. Okay, so we can, for example, so you can just like play it around, and if you had some evolution of your spin, like spinning around the z-axis, for example, this is like the state that you would. Oops. I don't know how I. Full screen. Oh. So as I was saying, you can again just be interested in looking at this block sphere as representing, for example, your spin 1/2 that you saw in NMR. You guys already went to the NMR labs, yeah? So for example, in NMR, what you're interested is in measuring, loosely speaking, for example, the polarization along the x direction. Okay, you measure probably sigma minus. I don't know what they taught you, but let's say that you more or less measure the polarization along the sigma x direction. So what you really want to know is what is my projection of my state vector along this axis here. And it's represented by this blue line there on the x-axis. So let's say that I start with my spin in the transverse plane along the x direction, and then I let it evolve. It's precessing in the magnetic field, so it rotates. And as it rotates, you can see that like the projection in the x direction is sort of changed with time. And correspondingly, this will be like the trace of the signal that you would get. Okay, just rotating at its particular frequency here. And of course, if instead of this, I have a different angle theta, well, what I have is that my projection here is smaller, goes between smaller limits, and correspondingly my signal here, it's also smaller. Okay. All of these, what I'm representing are still pure state. So even if I write it down, for example, in the density matrix form, but they're all pure states, so that the tip of my state vector there is always on the surface of the sphere itself. Okay, so we're going to see that when I start talking instead about mixed state, now I can sort of occupy all my sphere and also the inside of the sphere. Okay, so for example, we talk about this identity operator. Okay, what it would correspond on my sphere, the identity operator. Did you look at the block sphere at all or not? Yeah. So these correspond like to 0, this minus, 1. So what would be like your density, your identity operator? The center. Thank you. I don't know what everybody else said, but I heard here the correct answer, so like perfect. Yes. So what you're representing here is more or less this vector, okay, this changing vector, like projection in the x, y, and z direction. Okay, if you only have the identity part, okay, I wrote it down as I over 2 just to distinguish between 1, so it is still a matrix, then this part, this vector is 0. Okay, so if you have to represent it on the sphere, then it will be just the origin of the sphere itself. Okay, so we're going to see some more of this animation later on, which hopefully are a bit more interesting than this one. But okay, this was just to get you started with this type of animation. Okay, so I spent too much time in just talking about the prerequisite to decoherence, but now let's go and really talk about some decoherence. So we had this idea about our density operator as having lost some information to the environment. So what we have done until now is sort of a static picture of this situation, and what I would like now to introduce is more of a dynamic picture of this loss of information. So what we want is to study this loss of information from the system to the environment. It's too high. I'm writing going up, which I think it means that I'm an optimistic or something like this. When you write going down, I think it means that you're sad. I'm an happy person. Good. But it makes for very bad writing. Okay, so how do we study this? So the idea again is to have our total system, which we can represent just as a pure state. And so we know how to describe its evolution. Okay. But when this system interacts, the total system can be divided into the system of interest and some kind of environment. And what we really care is only about the system itself. Okay. So how can we then describe the evolution of the system alone? So what we know is that, well, if I have my density operator describing my system plus environment, then its evolution is going to be given by, this was the only formula that I told you they will come back. And so what is given by? U. Yeah. U, which is, again, system and environment, system environment. Okay. So what if I really interested only in the evolution of the system alone? What should I do? Do the partial trace. So by now we know everything. So I will do the partial trace of this. So what I'm really interested is doing the partial trace of this evolution here. Okay. But I would like to have some way of writing down this system evolution without having to describe the full evolution of everything of my system plus environment, because, as already said, most probably you don't really know all the things about the environment. You don't know how it evolves. So I would like to have a description of my evolution which bypass the environment and will just give me directly what is my density operator at the time t as a function of just what it was the system at time 0. So what I would like to have is rho s of t with some functional of rho s at time 0. Okay. So this functional here, because it's an operator which acts on another operator, so S is usually called a super operator. Okay, so operators act on vectors, vector states. So operators which act on operators are called super operators. So how can we then write down these super operators? What we can do is to start from this definition of what our state is in terms of the evolution of the system plus environment, and see if we can sort of simplify it with some assumptions so that we have an expression which will only depend on the state at time 0. Okay, so this is our first goal. So in this first goal, the assumption that we make is the following. So we assume that our state at time equals 0, so rho SE at time equals 0, is a separable state. Okay, so this is sort of an okay assumption because I can always define my time t equals 0 as that particular time at which my system and environment were in a separable state. So, okay, in one way or the other, I get out of it. So then this means that I had rho s at time 0, tensor rho e at time 0. Okay, and then we make another assumption, which is to say that my environment at time 0 was just in its ground state. Okay, so it was at equilibrium, and so it was like in its ground state. So what I really have is the following. And I will call ground state 0, which will have energy 0. It doesn't have to be like the 0 of a qubit. The environment can have many, many different levels. So it's ground state, it's 0 energy, so I call it 0. Okay? So environment will be described by some eigenstate k, and maybe we could have its eigenvalues ek. We're not going to really use them. So k can be 0, 1 to infinite. It can be like a very large environment. Okay. So now I just plug this into here, and then I want to perform my partial trace. So partial trace over E of U C plus 0 environment. Okay. So I'm doing a partial trace with respect to the environment. So this is the same as doing a projection on one preferential basis. So let's take this energy eigenbasis for my environment. Okay. So this is the same as sum over k, this same expression here, equals C 0. Okay. So this is just a different way of writing down the trace. So if you want, it's the definition of the trace. Okay. Yes. Sorry? Why the initial state like of the... So the initial state of the system doesn't have to be a pure state. So I assume that like initially they're in a separable state. So more or less what I'm saying is that at the beginning of time, my system of environment were separate. They didn't interact with each other. And so they were in a separate state. And I take that as my initial time. Okay. And then I say, well, what I want to study is how the coupling between them will sort of make my system evolve, and so will create entanglement, which I then disregard. So, I mean, this is just, if you want, is one way of defining the initial time is the time in which they didn't interact as yet. Okay. So why then my environment is in this ground pure state? Well, again, I can consider my environment as just to be like its own state, and at equilibrium it will try to be in its ground state, and so this is what is represented by. Okay, so how can I write down this in a more simplified form? Does this partial trace act on rho S? So what I can do is sort of to switch the order of this 0 and put it here, okay, because it doesn't act on rho S. So what I have is sum over k of k u s e 0 rho S times 0 0 u s e dagger k. Okay. So I'm just using the fact that what I'm doing here, if you want, is a partial projection, so the same concept as a partial trace, but now I'm doing like a projection onto the eigenstate of the environment only. That does include rho S, and so I can just like write it down in this way. So now I can take this and just give them a name. Okay, so I call them MK. And this will be just MK dagger. Okay. So now what I have is that my rho S at a time t can be written down in terms of a sum over these operators MK. And of course, like U S E was depending on the time t that I'm considering. So if you want, this MK will also depend on the particular time that I'm looking at my system. So this is just rho S 0 MK dagger. Okay. So I sort of accomplish what I wanted to do. So now what I have is that I can express what is my rho S at the time t just as a function of rho S at the time 0. Okay. The environment is not explicitly there anymore. Of course, it's hidden. It has to be hidden somewhere because it's the environment and the coupling with the environment which determines, in part, the evolution of my system. But now it's no longer like explicitly written down there. So if I give you a system and I tell you, okay, the operators MK are such and such, then you can calculate what the evolution is. You don't need to know what the environment was. You can abstract from the environment. Okay. So these operator MK are called Krauss operator. Okay, from the mathematician who introduced them. And this sum here is called the Krauss sum. Okay.
Can you explain how we get the second term?
So I want to calculate rho S of t, so I take the partial trace. Like here, it's okay, yes? So how do I get here? Okay. So what is trace? What is trace of an operator? Trace of A. Definition of trace. Is the sum of the diagonal elements, for example, if A is a matrix. Okay. In general, what you have to do is to take one basis. Okay, let's call the basis K, which I wrote down here. Okay, and then the trace is going to be the sum over all the basis element of K, A, K. Okay, these are all the diagonal element of this operator. Okay, so this is just what I wrote down here. Okay. So this is like the same stuff as before, which was in here, and I just wrote down my partial trace as a sum over the eigenstate of this environment only. So this K are the basis of the environment only. We go from 0 to n, let's say, infinity. Okay. Okay. So, yeah. Why can I move the cat? Yes. So, as I say, like with 0 and with k, they are eigenstate of the environment only. Okay. So they do not act on the system. They only act on either system environment, global operators, or they act on the environment. So, for example, they do act on a USE, but they do not act on rho s. So I can sort of move it wherever I want with respect to that rho s. Yeah, this partial projection, it's a bit tricky. But if you write it down explicitly in terms of like all the matrix elements, then it's more clear. But conceptually, it's because rho s lives in another space if you want with respect to the 0. So I can just take it out. Okay.
I just wanted to note that it might be clearer why you can move the ket if you keep the tensor product between the density matrix and the ket, so that it doesn't look like the matrix is applied to it.
So you're saying here what I have is like a tensor product like this, but then I just moving it out. So it's because like I'm doing like now this projection onto here, and so what I want to calculate in the end, so like what, for example, what you get on this side is an operator which is only now acting on your system. So the same way I can just write down like all my matrix in a different way, or my operator in a different way, so that I can reorder my states to have in the end just an operator acting on the system. Okay. Yes. I'm gonna give you like explicit example with like very simple things, so then you will see how these operate.
Yeah. Or in a trace E environment, can you like swap over USC and USE?
So you're saying, can I just put this here when I do only the partial trace? No, because otherwise they will go away. Yeah. Okay, that's not a good answer. I don't admit. If it were true, all my master plan to teach you something will fall down. But okay, that's not a good way of answering. But yeah, the answer is still no. It doesn't work out because what you're doing the trace is only on part of this USE, so you cannot completely rearrange the order of. You still like out of this partial trace, your USE are still operators, so they still do not commute. So you cannot like change the order of the multiplication. That's slightly better answer. Okay, where did I lose my notes? So, this cross operator have some properties. The only properties that I'm going to tell you guys is the following. If you have sum over mk dagger mk, this give you identity over the system state. Okay, and that ensures you that if you start from the identity operator for your system, then you're still going to be in that same state. So the identity operator does not evolve even in the case that you have decoherence. Okay. There are other properties of this cross operator, which more or less were only there because what you want to have is that at the end of the day, this evolved density operator is still a good density operator with all the properties that we said at the beginning: trace 1, non-negative, etc., etc. Okay. Remission. So you cannot have like any MK, you just need to have some with particular properties. The other thing which is interesting is that I have this evolution. I told you that my MK are these. I started to show that my use of whiteboard is bad. I'm always writing things all over the place. This is my definition of my cross operator. And what I did was to pick one particular basis, for example, the energy basis I told you, for in order to make this partial trace. But the partial trace as the trace is in the end the same whatever basis you're choosing. Okay, so I could have chosen like a different basis. So I could have found out here that my cross operator are given by an H, which is the partial trace of USE between the ground state and some other basis h, which might be a different basis, I don't know, your momentum basis or something like that. Okay. So this Krauss sum representation is not unique. You can have many different Krauss which still describe the same evolution. And then the two are linked by very simple relationship, one to the other. Okay, just up to a unitary difference between one and the other. But it's sort of interesting to know that you can have the same evolution starting from different Krauss operator. So we started by saying that what I wanted to achieve was something like this. Okay, so I want to be able to describe the evolution of my system based on what was my system at time 0 alone without any knowledge of what was my environment to start with. And I told you one fourth way of writing this down is in terms of this Krauss sum operator. So let me erase a little bit of things and just keep the important things. So let's say the first one is this Krauss. So you have rho s of t, sum over k, mk, s of 0, mk. Okay, and the mk's are given by k, USE 0, where what you have to remember is that this k and 0 were eigenstate or basis in general of your environment only. Okay, so I just put some E here just to remind ourselves that this is over the environment. Okay, there might be a different way or more general way of describing this. Okay, and it is in terms of more general super operator. Okay, so in general, as is written up there, rho s of t is going to be given by some super operator s times rho s at the time 0. Again, this super operator s has to have some properties. Okay, so these properties are there to ensure that you do have, at the end of the day, this good density matrix. So S super operator. Oh. So there's some properties to ensure rho s of t is still a good density operator. Okay. So what are properties? I don't even know if I wrote them down. Yes. So what are properties of your density operator that you want to sort of conserve under the action of S? The trace should be preserved, so you have trace preservation, trace preservative. I don't know if it's a good way of writing it down. Positivity, let me come back to that. So it also had to preserve the fact that the density matrix is Hermitian. Okay. There is another one which is linearity. It's not strictly necessary for S to be linear, but it is convenient. I'm sorry, I think that your neck at the end of the day will be straight. It is convenient because it sort of respects this interpretation of the density operator in terms of superposition of different pure state with probabilities. Okay, so if you don't have linearity, you might have some situation in which that interpretation is no longer true, and we sort of like to have it there. So yes, you want it to be positive. Even more, you want it to be completely positive. Which is a slightly more complicated version of positivity. We just say that if you consider a larger system, so if you take your system and then you consider a larger system on which you apply this super operator, then still, when you go back to your reduced system, you still are positive.
Can we just rephrase that by saying we want to keep it physical?
So I was going to say very mathematically involved. Again, you want rho s to still be a good density operator, which is you want it to be a physical density operator. Okay, so I mean you can look up all the mathematical properties, but the concept is that you just want it to still be a good physical description of your state. So yes, I totally agree. Forget about all of this. So in order to forget, I will quickly erase them. Okay. But if somebody asks you, well, I did it. I wrote it down once. Okay. Well, you have to respect the mathematics-oriented people. Okay. So why does so we have like these two ways, or if you want, of describing them, and there is also like a theorem which is called the Krauss theorem, just again by the same mathematician which wrote down this, which tells you that these two representations are actually equivalent. So whenever you have a superoperator which has this mathematical property which I just erased, maybe I should have kept it for 1 second longer, then you can always find a set of Krauss operator with which you can describe them. So if you want, what I'm saying is that the Krauss theorem tells you if S is a good superoperator, superop, then there exists always a set of Krauss operator Mk, so that S of rho can also be written as a Krauss sum, Mk, rho, Mk dagger. So the two representations, although slightly different, they can be made to be equivalent. And then there are even more complicated math that we want to forget the minute that we learn them, which tells you how to go from one description to the other. So why? So I say like we have two different descriptions. They are in the end equivalent. I can go from one to the other. But I haven't really told you why is this describing an evolution which will give me decoherence. Okay, so it might be that, okay, I have this Krauss sum, but I still get something which is totally coherent, and I've lost nothing to the environment. So why do you think that like this could lead to decoherence, this type of description? And why it would not? And when would it not? So let's take one example. Let me erase this. So what if I tell you that the propagator, like describing my evolution, is actually given by US tensor UE? Okay. What is going to be your Krauss sum for this particular case here? Or even more simply, what is just rho s at the time t? So, okay, I could try to go through here and then derive what is rho s. Or I could just say, okay, this is what I want to calculate. Okay, so I want the partial trace over E of my US, UE. My initial state, as I said, is the separable state, US dagger, UE dagger. Okay, so then everything is still going to be in a separable state. It's just trace over E of US, US dagger. Times UE, rho E, UE dagger. I take the partial trace, so I take this stuff out. US, US dagger, times the trace. This. Now, this is now just a total trace, so I can bring this on the other side. So this is just the trace of rho. Or in any case, the trace of rho, even evolved in time, is still just 1. So this is just equal to 1. And so this is just US rho, US dagger. Okay, so perfectly. So what it means is that if my evolution is such that the system and environment are not really interacting. They're just evolving independently. One is evolving with its own US propagator, and the environment is evolving the UE environment propagator. Then no entanglement is generated during the evolution at all. The system was initially in a separable state. It will still be in a separable state. And so this partial trace, which is nothing else than the same as this cross sum, will be just given by this last term here. So in other words, so if USE is equal to US tensor UE, my cross sum reduced to just one single element of the sum and this MK will just, this only element of my cross sum MK will just be the propagator US. Okay. If instead I do have a USE which is not written like this, then I will have for sure more than one element in my sum here. Okay. And then, of course, I will not be able, so if I have this, of course, I can reverse my arrow of time and just go back. So unitary evolution is reversible. Okay. But if instead I have this sum over many different MK, then there is no operation which can bring me back in time. Okay. And so my evolution becomes irreversible. So what you have is decoherence. What you have is that you are creating some entanglement between your system and environment, because now you have some coupling between the two, and so you have exchange of information, if you want, from the system to the environment, and then you're disregarding all this information which has leaked into the environment. And so you only look at it when you only look at your system. So in that case, when you have more than one term in your cross sum, you do have decoherence. Okay? Questions? Yes?
Is there a way to disentangle two systems if you don't know how they evolve?
Oh, I was going to say, well, in general, yes, there are ways to disentangle system. If you know how they evolved, you can apply the inverse operation. But if you're losing information about how that entanglement was formed, as it is normally the case with the environment, then it becomes impossible. So, and that's why, like, this lack of knowledge sort of brings you decoherence. So in sometimes, like, your environment is maybe just like one or two other qubits which are out there, and they're interacting together, but, well, maybe you don't know how they're interacting, so you're losing that information about them, and you see it as a decoherence. So if you kept all the information about these 2 or 3 other qubits, then you could sort of bring them back into a separable state, and then you wouldn't have decoherence. No other questions? So let's look at some examples. So the first example is going to be just spontaneous emission. Okay. So we have just a 2-level atom, just to simplify my life. And what we are assuming is that my 2-level atom is my system, so it can be either in the 0 or 1 state, let's say, so ground or excited state. And then if it's in the excited state, it can emit 1 photon. Okay, if it's in the ground state, it cannot. And we are assuming that we also have, if you want, the photon field, so if you want, like, the EM field. And just to simplify our life and keep with qubits, also the EM field is just represented with either no photon or 1 photon. So I can also just write down this as 0 or 1. Okay, so this is atom. And the atom will be my system. And the photon, well, the photon sort of, when it's emitted, might escape. And I assume that I have no detector. I have a very lousy detector, and so I cannot know when the photon has been emitted or not. So this can be considered as an environment. Okay, it's a very minimal environment, but because I lose knowledge about the fact if there is one photon or not, is still a good environment because it sort of represents my lack of knowledge. Okay. So what I'm saying is that if my atom is in the one state, then it can decay and emit one photon, which then will be in the one state. If it doesn't emit any photon, my EM field is in the 0 state or vacuum state. Okay. So how can I describe sort of this evolution? Well, I know that if I'm in the 0 state for the system and 0 for the environment, then my evolution can only be what can I have at the end of the time. Still the same. Yeah, perfect. I cannot change anything because I cannot jump. I don't have any photon there and start in the vacuum, so I cannot jump to the excited state. If instead I'm in the one state for the system, and I'm still assuming that at the beginning of time my electromagnetic field is in the vacuum state, so in 0, then I have two possibilities. Okay. With some probability, I do emit a photon. And so I will be in the state 0 as 1 for the environment. And with some probability 1 minus p, I will still be in the initial state, 1s, and still have 0 photons. Okay? So these are the two possible evolution that I can have, depending on what is my initial state of the system, and I'm assuming that my environment is always in the vacuum state. So what are going to be the Krauss operator, which describe this process? Okay, so the Krauss MK, we say that these are USE 0. Okay. So here I haven't really given you an explicit propagator, if you want, but I just described how the system evolved under that propagator. Yes?
Does it have to be like superposition of, can it be like probability distribution, like the classical probability distribution of whether these two states are just happen?
So what I'm assuming is that my system plus environment will form a closed quantum system. Okay? So what I'm representing there is if I have one S0E and I'm evolving it under a propagator USE, what is going to be this state? This state is pure state. Under unitary evolution, you still have something which is going to be a pure state. And in particular, what I'm saying is that it's given by this superposition here. So it does have to be a coherent superposition in that case. Yeah. Because I'm still considering like a closed system with system plus environment. Okay, so what are the Krauss operators? So first of all, how many Krauss operators do I have now? Louder. 2, yes, because I only have 2 states for my electromagnetic field. Okay, I could have told you, okay, I could have emitted 1 or 2 or 3 photons, but for simplicity, either 0 or 1. So I do have 2 Krauss operators. So the first one will be let's call it M0, 0, USC 0, and the second one is M1, 1, USC 0. So let's start first with this one, which is actually easier. Okay, so what you want, you know that USC 0, what you have to look at is how this propagator acts on your initial state here. Okay, and then see in which case do I get my environment to be jumped into the one state. Okay, so there is only one term in here in which my environment has gone into the one state. Which one is it? This one here, yeah? Okay, because I have one here. So, well, okay. What I have then is that I just have this probability P, but then I still need an operator which is acting on my system. Okay, so what does happen to my system when I'm getting my environment in the one state, so when I emit one photon. So what I had, which was at the beginning, I was in the 1s, and then now in the 0s. Okay, so I need an operator which makes this jump for my system. So what I have is that my operator will be just this operator which takes the system from the one state and brings it down to the ground state, 0. Okay?
Couldn't you just use sigma x?
This is sigma plus.
Okay.
Only. Yes, I could write it down in that way. Okay. Is it sigma plus or sigma minus? Isn't it sigma minus? Because it goes down. It depends if you consider 0 or 1 to be. I never know which one is supposed to be the grounded and statistic. I should know. Okay. Is it clear how do I get it or not so much? Yes, ask question. Why isn't it the other way around? So because what I'm starting is, so what I want, if you want, was that if I take USE 1 S0E, then what I'm looking at is what is the state here, which is 1E. But I know that the only one which corresponds to 1E is with 0S. Okay. This is the only term which will give me a non-zero value, and then I just write down sorry, these two, so I can 0S 1E U 0E, and I have 1S. So as you can see now I can sort of swap the order of my projectors because I only want this partial projection on the environment. This one is now my state, my Krauss M1, and then I want this M1, of course, to have a non-zero matrix element between my 1 and 0, and so this is given by this 1 and 0 here. So it's a different way of writing it down. Okay, so what is now M0 if M1 is clear enough? So I have two ways, if you want, to have my environment stay in 0. Okay, one way is if my system was in the 0 state. Okay, and another way if my system was in the 1 state but it just stays there. Okay, so in the first case, well, here I just have 1, so I have 1 times the operator for the system is just, well, if it's 0, it will stay in 0. Okay, and then I have then this other term here, 1 minus p, which will just give me, in this case, now again, if I was in the 1 state, I stay in the 1 state, so I have 1 S. Okay. So this way, I explicitly built up my Krauss operator for this simple particular case of a spontaneous emission from my two-level atom into the vacuum state of the environment. Again, you could think that if you have a detector, you can measure if you did have a photon out or not. Okay, so if you do have a detector, okay, and let's say that you do measure 1 photon. What is your state after this measurement, the state of your system? So it will just be, well, the ground state. Because you know that, well, if you were in the 1 state, you emitted something and you went down to the ground state. And in some sense, you also know that before like the measurement before the emission, you also knew that your state psi s at time 0 then will just excited state 1. Okay. So if you do measure the state, the photon, then you're not losing information. So the environment is not really an environment. If you want, it's a measurement apparatus. And so your state, even after the evolution, was a pure state at the beginning and is still a pure state at the end. Okay. If instead this photon is lost, you cannot measure it in some way, then your state, so if you cannot measure the photon, then your state after the emission has happened, or maybe did not happen, is given by the Krauss sum here. So it will be sum over k equal 0 or 1 of your mk rho s at 0 mk dagger. Okay. And in this case, it's particularly simple, and you only have two particular. You only have these two Krauss systems. Okay. So we can sort of write down explicitly. Is it that late? Okay, it's very late. So you can write down explicitly what this will be, and what you get is that if you start from any initial density matrix, rho after this emission will be given by rho 0, 0, 1 minus p rho 0, 1, minus p rho 1, 0, 1 minus p rho 1, 1. Okay, with this p is like the same probability here. And this will be after we wait for like a unit amount of time to see if we have an emission or not. Okay, if I wait twice, so if I wait for some time, this will be my state, and then I sort of apply again my Krauss sum to this initial state, then what you get is that you will have something like rho 0, 0, 1 minus p square, rho 0, 1, square root of 1 minus p, 1 minus p square, rho 1, 0, 1 minus p square, rho 1, 1. Okay. So you can see that if I have k, if I wait for k times of this process, what I will have is that my final state looks like 1 minus p, square root of 1 minus p to the k, and the diagonal term is 1 minus p to the k, rho 1, 1. Okay. And I can also say, well, okay, I can take an approximation in which p is short, so I write it down as some rate times gamma delta t. And so you can write it down this as a continuous function of time, and it will look like rho 0, 0, e to the minus gamma t over 2, rho 1, 0, rho 0, 1, e to the minus gamma t over 2, and rho 1, 1, what is it? E to the minus gamma t. Okay. So after, if I wait a long time, all these terms here go to 0, and you only have rho 0, 0, which just correspond to the fact that for sure at the end of the time you will be in the ground state, having emitted a photon. Okay. So, because I'm short in time, I will introduce another example and then show you how these play out in real life with animation. So the second example is something which is very typical if you want to decoherence. Okay. So what we have is environmental scattering. I can call it this way. Okay. So it's something which sort of happens to any macroscopic object. Okay. Let's say that we have a dust particle. Dust particle are macroscopic. Okay. I have my speck of dust particle. And it's sitting in the air, not today, but usually you have sun, and so you have a lot of photons, which will scatter on it and sort of go away, scattered in a different direction. Okay. But you don't really know all these photons, what they do. Okay. So the information about even the position of this dust particle is sort of lost because you don't know where the photons are coming from and where they go. And so there's sort of, you have your environment which is trying to measure the position of your dust particle, but any other information about the energy, or more particularly the momentum of the dust particle itself, is lost because you cannot really detect what is this momentum exchange between the photon and the dust particle itself. So your dust particle sort of decohere, or it's projected out the same as in a measurement that you have collapse of your wave function into a position eigenstate, so you can know where the position is, but you don't have any information about your momentum state in a quantum mechanical sense. Okay, so this is sort of typical of why we sort of observe mostly just classical properties for any macroscopic object, because even if you try to be in a very controlled environment, you will still have, for example, photons or other dust particle or many different environment entities around it, which will try to measure again and again and again, but you are losing all the information about this measurement that the environment is doing. Okay, so we can sort of describe a bit this type of problem by, again, by looking at a system given by our dust particle and this environment of our photon. So in this case, because I do want to have a photon to start with, so I can have a photon in its ground state, 0, or in some excited state if it's interacting with the particle. And in more particular, I have at my dust particle, again, it can be either in its ground state or in its forced excited state. And then if it's an excited state and it does interact with a photon, then the photon can either stay in its initial state, in its same energy level, 1, or it can sort of be promoted to a higher energy level, 2. Okay. So it's like energy level for my state, for my environment. So if your particle already has some energy above its ground state, it can sort of give some energy to the photons with which it's scattering. Okay. So more precisely, what you can have are the following cases. So if you have that, you have your system in the ground state and it's interacting with a photon which is initially in its ground state, then what you can have is that with some probability, 1 minus p, you don't have any scattering at all. The photon is not touching your dust particle. And so you just stay in the same state. Or with some probability p, it will instead have some scattering, but because the energy of the system is the ground energy, so it's low, then I can only be promoted to its forced energy level. In the process, your system is not really changing its state, because here we are talking about a dust particle which is big enough, so even in impact with one single photon, it's not going to change its energy. Okay, it's too big. If instead the dust particle was in the one state, and the environment is still in its ground state, then again I can have no interaction at all. So no scattering is happening, so the system is still in the same state, and this goes to the, it stays in its ground state. But if I do have an interaction now, then my system still stays in its same state, but it can give a bit more energy to the photon. Okay, so the photon now will go into the second energy level. Okay. So I guess I should write it down this way. So these are like the two processes which can really happen. So how many Krauss operator would I have now? So
why it excites to?
So like the assumption is that if the system has almost no energy, so it is in a ground state, then it cannot give energy to the photon. So the photon scatters, so yes, it still go from 0 to 1, but it's in the fourth energy level of the photon. So scatter the photon as low energy. If instead the system is in the fourth excited state, then the scattered photon has high energy or higher energy.
So where's the additional energy?
So like the assumption is that the particle is too big, so it doesn't really change its own energy, but still you can sort of give a bit of that energy to your scattered photon. So it's because the particle does have a bit more energy that you can say the photon has a bit more energy. So it's not like it's a cartoonish picture. So I'm not like conserving all like exact energies, etc. So it's still in the approximation where my dust particle is so big that even if you have like a small collision, it doesn't really change its state, but still you can promote your photons to a higher energy.
Like the probability for like scattering when the particle is in high energy state and low energy state, like does it have to be the same?
It doesn't have to be the same, sort of just simplify the picture here. So yeah, it could be different. So I'm just saying that this is like the probability of scattering. Usually, like if you just consider like a collision, it doesn't depend if your state has a higher energy or not. It's still the probability of collision is the same. But yeah, I mean, in theory, it could be different.
I'm missing the one we're not adding the transfer from 0 in our environment to 1 in our environment in this second. Why did we suddenly jump to 2 instead of 50?
So what I'm saying is that if the system is in this excited state, you can sort of give a bit more energy to your photon, and so the photon directly jumps to the higher energy level because it's sort of taking a bit of the energy from the particle dust itself. So I mean, as I say, this is like a cartoonish picture which sort of give you like the basic idea of what could happen. So how many crossband do we have? How many crows do we have? 3. So it just depends on how many states I'm assuming for my environment. Okay, that's how many crows you will have. So I'm having a totally cartoonish environment. So I'm not saying that this is like the exact picture, but I'm just modeling this event by just saying, well, I have only 3 possible states from my environment. And so based on that, I will have 3 possible crow states. So there will be just my 2 USE 0, 1 USE 0, but you also have 0 USE 0. So just staying in the same place. And what I get is that this one is 1 minus P identity, because if I have no scattering, which happen with probability square root of 1 minus P, so probability 1 minus P, then my system doesn't change at all. Okay, so I still have the same state in identity. Okay. If instead I do have a scattering, then depending on what was my energy, well, this happened with probability, which is just P for both of them. But in one case, this one, I was in the one state, and I will stay in the one state. As I'm saying, like this scattering do change the state of my environment, but the system is not really changed. Okay. Still, when I look at the information that is lost to the environment, then I do see an evolution of my system. Okay. So if I look at here, as you see, like the system was in 0, it's still staying 0. If it was in 1, it's still staying 1. But because some information is lost and given to the environment, then when I look at this evolution of the system under this Kraus sum here, with k going from 0 to 2, then I do see that I will have some evolution of my system. Okay. So how do I calculate the Kraus? So again, like it's for example, let's pick this one here, between 0 and 2. So what I want to do is look at this expression and see, is there somewhere in here where my environment has become 2? And this is the only term that I have here. What did happen to the system in that case? Well, it was in 1 and it's still staying 1. So I need to put this operator. Okay. So in some sense, I don't give you like here the full propagator because I only need to define it for the initial state of the environment given to being in the ground state. So the full propagator, if you want, I actually wrote it one version down here. But it's not particularly important. And it's not well defined. I mean, I could write down many different propagators which still give this evolution. But the game, again, is just to say, OK, this is the term which gives me an environment in 2. Coefficient is square root of p. And the system was in 1 and stays in 1. So the operator must be 1, 1 for the system. Same for, for the 1. Then the term will be this one. My system was in 0, and it stays in 0 with square root of p. And this is the term. For the 0, then I will have to sum what are these 2 here. And this will give me like the identity coming out of sum of 0, 0 plus 1, 1. So this is how you do again. OK, so we have like all of this. And we can, again, look at what would be this rho S of t. So what you have to do is to explicitly write down this as a function of this Kraus operator. Okay. So again, you can sort of have an intuition of what will going on. Are going to be like the terms on the diagonal, are they going to change in any way? So because like here this is an operator, so it's 1, 1 as projector. So if you are already in the 1 state, it's not going to change. If it's 0, it will just go to 0. Identity is not going to change. So the diagonal element here are not really going to change. The only thing that are going to change are the off-diagonal element, which will be then multiplied by this square root of p here. Okay. So what I have is that if my initial state was like rho 0, 0, rho 0, 1, rho 1, 0, rho 1, 1, then these 2 will stay the same. And these other 2 terms will be just multiplied by 1 minus p. Okay. Again, I can do the trick that I did before to say, well, p is going to be given like for small time by just some rate at which the collision happens, time a small time delta t. So 1 minus p, I can approximate it as the exponential e to the minus gamma t for longer time. So what I really have here is an exponential decay of my diagonal terms. Okay. So this is what is most commonly thought as decoherence. So what you have is that if you have an initial state, which was, for example, for the system, some superposition. Let's take the easiest one, okay? 0 plus 1. Okay, so your density matrix representation of this is just going to be given by 1 in all terms here. Okay, with 1 over 2 here. How does this evolve in time under this particular decoherence process? Or if you want, if I go for time which are very long, what is my final density matrix as time goes to infinity? Yes, so it just go to identity over 2, or like 1, 0, 0, 1 times over 2, because these 2 terms are just cancelled out. So what I did was I had a coherent superposition. I had a very mean environment, which is keep interacting with it and trying to measure it, but when I don't know what information environment is extracted from my system, but information is lost. And so all the phase coherence that I had in my system here get completely lost, and what I have in the end is just a complete incoherent superposition of the two, which has no phase coherence anymore, so it's, my system is decohered, and I have lost any information that I had on my system. So this is really what is the most canonical decoherence, if you want, because it's really, what you're losing is really the phase coherence in your system. So this one is my representation, block sphere representation of the two-level atom that we had discussed in terms of the spontaneous emission. So initially, you have that any general state of this atom could be anywhere on the surface of the sphere. Okay, so this is represented my sphere, and like the red lines are sort of all the possible points of your sphere. And now, what I have is that I put some rate of decay, gamma, or the probability of decay, and then I start applying in successive steps my cross map. So this is for 0 times of application, and then I can apply it 1 times, and you see that it starts going down 2 times. Oops. I say my computer is not very fast. 2 times, the sphere is shrinking. 3 times. Let's see if it goes. Let's see, maybe I can play it around alone. It's playing. It's not playing. As I say, I need a new computer badly. It shrinks. You can see it's going down toward the bottom, which I guess it represents 1, so it's the opposite. Should I go up? Which one is 0? Which one is 1?
0 is up.
Huh? 0 is up?
0 is
so 0, okay, let's say that at the bottom, let's define in this way. This is the excited state. This is the ground state. So it does represent my decay. So yes, so I'm shrinking and shrinking and shrinking, and let's say that I put a higher probability of doing the emission, and then you will start shrinking down faster, and at the end of the day, what you've done is that you will go down just to the ground state. Okay. So you just have the ground state. So what is interesting here is that I could have started actually from a mixed state. You don't have to start from the pure state or from the excited state. You could have started from an excited state, and then through this process, you always go down to the ground state. So what you can do is, through decoherence, actually prepare a pure state. So it's not that decoherence always have to be starting from a pure state and going to a mixed state. It could be actually the opposite. Okay, but you're still sort of losing some information to the environment. That's still possible. The same process can be generalized, and for example, you can have a different fixed point. So for example, let's see if I can put this. I put it 0. Then you will just go down and sort of shrink toward the origin. And so what you're doing is, in this case, really losing all information about your state. Okay. So this is this process. So I describe it as spontaneous emission, but it's more generally called amplitude damping. Okay, and going to different fixed point is called generalized amplitude damping, and you can find it. Nielsen and Chuang book is like called in this way. Okay, the second example was how did I call it? I think it's this one. Yes. So this was the second example in which, as I said, I had this environment continuously monitoring my my system. Okay. So in this case, what we expect is that we will have our sort of x and y part of my block sphere to start shrink down, but the 0 and so now I can call them again 0 and 1 state. They're not really changing. Okay, so what I expect is my sphere to shrink down around the origin in this way, and this is hopefully what happens. Let's see. So you can see that, again, I'm sort of doing continuously in time with exponential decay on my sphere, or the state along the x and y, so these coherences are shrinking down. And the only thing that in the end, what I get is that the z part are, the longitudinal part are conserved, and so I still have possibly an incoherent superposition between 0 and 1. Okay. And I can have actually a similar model. Let's stop here and go back, in which instead of having just this type of decay of my transverse component of my block sphere, I can also add this gamma 1, which is decay also of the longitudinal component of my z component. And then what you expect is, of course, that the sphere will all shrink down altogether, but you still have that your transverse component are going to shrink down faster, or twice as fast, as the component along the longitudinal axis. And that's mainly just to conserve energy, so that's like why you have that. So how does this play out, for example, if we compare this to what you can see, for example, in NMR? I think that I have this one. So in this case, what I have is something similar to the simulation that I showed you before. I should erase my 0 and 1. Okay. So what we saw before was that if I had my block sphere and I start with some state, then as a function of time, I will have some precession. Okay. And the signal that you get from, for example, projecting along the x-axis is some cosine function of the frequency of your spin, for example, in NMR. But now what we can have is to add some decay. Okay. Oops, stop. So let's say that I had some decay, and for example, only the transverse component start decaying down, and as you can see, my z component is fixed, in this case 0.5, but the x and y component shrink down, and so you can see that the block vector starts going inside and shorter and closer to the z-axis, so representing a mixed state, and correspondingly you have a decay of your signal, okay, with an exponential decay as your envelope. And then I can also add some longitudinal relaxation with gamma 1. Pause. Go back. And now you will have it not only your x and y component become smaller and smaller, but also your I guess this is wrong. Your z component should become smaller. Okay, I didn't print it out in the correct way. But this red line actually does represent your z component, which is also decaying down. So in this case, what you see is that what you're decaying down more and more, and in the end, for this particular case, my fixed point is just the origin, so I'm canceling out all my polarization. Okay, and so the last point is just like the origin down here. And also my signal has completely decayed there. Yes? So gamma 1 is sort of, if you want, is related to like this example that I show you about having this collision, if you want, of your environment with your system. So what it does, if you remember, the state of your system was not changing in the collision itself. If it was in the ground state, it will stay in the ground state. If it was in the one state, it will stay in the one state. Okay. So this gamma 2 sort of is a process which still conserves energy for your system itself, but is losing any coherence between the energy levels. Okay. Instead, the gamma 1 process is a different process, more similar to, if you want, to spontaneous emission, in which you do have a jump in the state of your system, so you're changing the energy of the system itself. The two processes, of course, can happen at the same time because of different interaction with the environment. And when you combine them, so you have both this gamma 1 type of decay or gamma 2 type of decay. The first one change your energy, gamma 1 change your energy, while the second one only raise the phase coherence of your system. So I think that I'm way over time, and you're kind enough to stay here. Yeah. But yeah, I shouldn't abuse too much. So I didn't really cover everything that I wanted to cover, not even close. But I hope that it was still helpful in some way and interesting. I have some lecture notes which I have from a class that I teach at MIT, so I sort of extracted some of the part that I wanted to explain today, so I can clean them up and then maybe give it to Martin, and he will have it. So I have this stuff here. I can also give like these are like Mathematica simulation, and you don't even need Mathematica. You can download the Mathematica player, which seems that everybody knows, and then you can play around. If I don't know, I found them fun, also fun to make. So sometimes I make some extra one, and then students are like, "Why do you make these? This is stupid." Like, okay, I had fun making it, but I don't know. I think that like sometimes like visualizing like this, like what happens to your system is just like more intuitive than me writing down too many equations. So, question? Otherwise, thanks for listening. You had question? No. Any question? I think that there is lunch waiting for you outside. So.